All right, hi everybody. Welcome to FEA 101. Hopefully you guys can hear me. All right. Hey, so I actually see some familiar names. Danielle, are you with the VETS team with the senior design? All right.
Yeah, it's me.
All right, good. Yeah, very good, very good. I see you probably have some FEA stuff you kind of want to discuss later.
Yeah, just kind of getting the thing I'm
Right.
struggling with the most is just like printing off the PDF with like all the results and everything.
Okay, got it. Got it. Yeah. And then I see Rachel. All right. Also with the VETS team. All right. Let's get started with the FEA 101. Yeah, so welcome, and then hopefully you guys can see from the screen. If you're not, let me know about it, because right now I actually can only see from my PowerPoint itself. Yeah, so one of the interesting part is that if you go Google FEA analysis, and what usually this classes is offered as a graduate level classes, and not to say that to kind of stop you guys from, doing simulation and stuff, but actually I really was very happy for you guys to kind of enroll in this 50 minutes class, and I don't want to kind of stop you from doing it. In the past, when I learned FEA, was very struggling, and so is my colleagues. When we learned this, there's really not much of information out there to kind of guide us, like what is the correct results and what is the wrong result that we shouldn't do. So today, I'll do my best for 50 minutes to kind of talk about what to do, what not to do, and then what is the tool out there that we can kind of play around. Right. So yeah, so to kind of inspire you about FEA, right now the current technology that we can do is really unlimited. It just depends on what sort of results we want to get in, and kind of sarcastically about doing simulation. A lot of people usually would say that garbage in and garbage out, because the computer that you're using, it's not smart enough to kind of adapt like what kind of simulation model you want to kind of forecast. So here's just some of the results to kind of show you. You have like water droplet heading on the membranes. And then over here, you can see this like a bullet. It's like a supersonic speed kind of heading into a water. And then hardness test that we're doing. So actually, I'm a material science major, and then this is some kind of very cool to kind of, you can predict what is the hardness material. Just in case you don't know what hardness is material that resistant to plastic deformation. And then over here you have, if you're an ME major or you're aerospace and IE, this is like a flow simulation analysis. And over here you have a two-phase flow flying into a cyclone dust collector. You separate the particles and the flow and stuff. And over here you have casting. So by the way, in the past, I was also one of the TA, and as for now, I'm also a TA. But in the past semester, was the TA for MSc Bronze, AT, and CAUS, and the VETS team. And then you can see for the MSc Bronze casting, a lot of time they struggle is where do they want to put the runners. So basically, what runner is where you want to pour in the liquid aluminum and then fill the empty cavity of the mold itself. So you can see the aluminum that's filling the cavity over here, how it sort of flows. So you can therefore predict, okay, where it's going to solidify from the beginning to, so that you can avoid any cavities and voids that kind of are forming. So over here, you can see how the voids form. So if we're pouring at the beginning over here, you can see it's probably going to form at the kind of back of you. So actually, that's what simulation is supposed to do. In the past, actually, I would show a video, but today I'm just gonna jump that. So right, so for the FEA 101, here's some of the resources that's available, and then for sure I'm gonna send out the slides to you guys to kind of know where did I get all these resources. So what is FEA is actually this video, what I was about to plan to kind of show you guys. And then today I was planning to kind of demonstrate how I do my bending and then tensor coupon over here. And the reason why I'm showing bending and tensile, these are two of sort of ASTM standard they typically do for testing. And then I think to kind of show you the concept, and once you know, you will know how to kind of apply these kind of theory into a more sophisticated geometry or model, and then so on. So over here, I also put a SolidWorks simulation tutorial for beginners. So again, I don't work for Solidwork, but the fact that I just use Solidwork a lot as a base, so basically I'm more familiar with Solidwork. I know that there is like Fusion and then all other software out there that you can use, and they pretty much can do a good capacity of simulation. But the thing is, as long as you're familiar with it, go ahead and use it. I mean, pretty much the theory behind that is pretty much the same, so no surprises. Here I posted a frame stress analysis tutorial, and I'll see if we have time. I want to kind of get into that to kind of show. So a lot of teams do a lot of like these frame stresses analysis and stuff, and I think it's very common. And this is just one of the link I found on YouTube. You can use it later. And free SolidWork over here. So the Purdue itself do provide free SolidWork, and if you go onto this website, Engineer Purdue EDU PUOS, enter and then key in your Purdue account, you can download a free SolidWork for that. And again, there's as much as other FEA software out there they promote for free, you can also use that. So material selections. Let's double check if I'm recording. All right, so I have to record this, so perfect. So getting into that, one thing is if you have any questions, just feel free to interrupt me, because the way the Microsoft team is set up is I cannot really see like the chat room and stuff. So any questions, just interrupt me. That would be the best way. So right over here is the material selection. So one thing is, before I start doing some simulations and stuff, I think some of the clear idea that we have to understand is what material we're using, so that when it output the simulation results, it makes sense. And then again, the simulation model actually doesn't tell you if it's correct or wrong, or if it does obey to any physical laws. So you have to keep in mind that, okay, does it make sense or not? So I guess what I'm trying to say is I pretty much listed some of the materials over here. And these are common material that we use: iron, steel, stainless steel, aluminum, copper, wood, and then so forth and so on. And I think at this point right now, I think it's a common knowledge that, you pretty have a much of a sense of, for example, iron, it's more have a higher strength for typical aluminum and copper. So aluminum and copper is more softer. However, we compare aluminum and copper compared to plastic, it is more harder in a way of saying. So on the left-hand side, I listed the y-axis as the Young modulus, and over here below is, can't really see, that's blocking. Let me jump that. So yes, yeah, so it's density. So the axis is the density. So there's a trade-off over here when you choose a material, right? So if you go with a higher Young's modulus, and then if you have a higher modulus, meaning that you have a high, high strength material, and then basically if you come over here, meaning that you have a high density, meaning that the material is more heavier. And the point of over here, if you can see my mouse like I'm rolling around here, there's no material over here. So there's no like, oh, if you want a high Young's modulus, again, that's higher strength, and then you want to have a kind of less of a weight, smaller density, there's no material for that. So this is a trade-off. So if you want to have a lighter material, then the strength of the material basically is weaker. And so goes as if you have a higher strength of material, then the density is higher, then it's gonna be more heavier, right? So that's kind of mind that you have mindset there, kind of memory when you do this kind of simulation. So over here on the right-hand side, here I listed the strain and stress. So a couple of few concepts when you do these FEA analysis. Stress, just kind of recap your memory. And for sure, I know a lot of you probably know, stress is force divided by area. And strain over here is the displacement, where you pull a opponent over here and the displacement increase. And then if you release it, it recovers. So a couple of few, engineering terminology, and then I'm going to continue to emphasize through on. Over here, I have listed a couple few points. Here is the yield point. Right over here, this dot over here limit and yield point over here. So this is important because what happens is when you do a tensile bending shear and whatever forces you're applying, and eventually, if you pass this yield point, it will not recover. So basically, it will in a way deform forever. So think about like a rubber band, and when you extend it long enough, it's not going to recover. But as long as it's within that region, it's able to kind of recover by itself. So the same concept go with plastic, wood, metals, whatever the material that you're using. The yield point is important. So usually when you design a material, especially when you use Solidwork, and I'm going to show you later, is this is the point where you want to kind of carefully look into that it does not pass this point, because once it passes this point, meaning that likely your material will be heavily deformed. Not that saying that's going to break. It's not going to break. Till breaking, there's still a few strain that you have to, couple of force you have to apply till it finally fractures, but there's still some time. But usually for industrial, considering about how this design is the yield point we're looking at. So that's the important part. So we have the fraction point over here and then breaking stress. So we'll talk about that a little bit later. And other stuff I want to talk about is you see this region here. I'm like coloring with a blue, and then plastic region I talk about. So the area over here, if we sort of do an integration, the entire area over here basically is the material. So I know some of the design, what some of the teams when they do, they consider impact and something that you fracture, you quickly hit onto it and then it fractures and break. So that's sort of a energy absorption thing that we look into. So I guess what I'm trying to say is this under this area, and this, if I can see, I can get the. So there's a lot of stress strain curve you can do over here. So it depends on the below area. Sometimes you get different curve, and below this area over here, if you do integration, the more area you get, basically it's saying that the material can resist impact more better. So that's one of the things you also should consider when you're designing a material. So yeah, so mechanical properties for every engineering should know. And again, this ties with FEA simulation because a lot of time it's a headache. It gives you a lot of numbers. So stress strain and then strength, you have compressed strain, shear strength, tensile strength, and elastic strength. So today what I'm going to do, I'm going to do a basic tensile strength. And then I'm also going to do bending, and surprisingly, bending strength and tensile strength is completely different. And that's why when we do these tests, we don't usually just do one side, one direction of loading. We do multi-axis of loading to kind of see, okay, what's the output of the stress and strain of the loading itself. And then we have stiffness, Young's modulus, hardness, toughness. So toughness, basically what I mentioned is another way of saying impact. So again, it's the area down below over here. So that's the toughness. So the higher of the area the stress strain curve covers, meaning that they have a higher toughness. So just think about metal and then wood itself. And then when you punch into a wood, I mean, you get hurt, but you can punch inside a wood, right? But for metal itself, it's a high toughness. So you punch it, it's not going to deform much. And then elasticity and then plasticity. So elasticity is able to recover, plasticity is it's not going to able to recover. Okay. So yeah, so this is I didn't make this up. Is mechanical property that every engineering should know about this. Okay, so one of the like questions I typically get is designing, and I just want to quickly talk about this. Is also tie with your FEA analysis. So a lot of you first design a model, right, and then you 3D printing. And one of the things I keep saying is that it really depends on how the 3D printing when they print the directions. So a lot of people would jump into the conclusion saying that, hey, the material is not strong enough. And then, oh, it's, it failed because, okay, POA is very weak and it's not able to endure the force that we're applying. And that's partially true and then partially not true. It really comes down to how the process that you kind of manufacture and affect the final properties. So you'll get what I'm trying to say is, for example, I'm just going to take one of the number and to kind of compare. So breaking strength. And what doesn't mean a breaking strength is when you apply a tensile strength and when it breaks. And forget about the units over here. Just look at the number itself, and then that's the printing directions we're printing of itself. So this is 29, and then 30, and then 30.8, and 29. And then moving forward to strain at failure. So just think about this as a displacement change. You have an 8 over here, and then this one, when you print at 45 minus 45, it is 5. So my point of saying is that don't quickly jump into the conclusion saying that, okay, when we 3D printing such as any polymers, it is not strong enough to endure the forces you're applying. Yes, POA and any polymer itself is pretty weak by itself, no doubt, when you compare it to any metals. But for now, for a proof or prototype concept, to show that it's able to endure the forces, it's actually able to do so. You'll be surprised. It's just simply the fact that how originally when you design your components, the way that the forces apply and how the process when we do the 3D printing, the nozzle that's used, cause it's not able to 100% to show its potential, okay? So what I'm trying to say is when you print something from EPIC itself or when you design something, you assume when you do a simulation model, you will output like, oh, you have 100 MPa. But in reality, when you design, you probably get half of it, 50 MPa instead of 100 MPa. So don't get kind of deceived by, okay, the material is not strong enough. It depends really what kind of material you're selecting at the final. So Young's modulus, so again, just think about that's the strength you're applying, yield strength, and then ultimate strength and strength at failure. And then strain energy density I mentioned is how toughness that is kind of correlate with that. So yeah, so CAD, I use a lot about Solidwork, and I know some people use Fusion 360, probably because you use a Mac or any computer, but that's also fine. CATIA Pro E, and then I use heavily with EPICS that do simulations and stuff. So watch out for which version it is. A lot of times when we look into everybody, some people may forget about what's the unit they're using. Is it either SI unit or inch unit? So you also want to watch that closely. What is it kind of compatibility with different versions and softwares and stuff, and then generate G codes and stuff. So yeah, so getting into it is finite element analysis. So I want to kind of talk a little bit more about this. A lot of people, they do finite element analysis, and actually for sure out there's tons of a job that's also related with finite element analysis, and a lot to do with civil engineering that they do. And the bottom line is the reason why they do is they want to predict where the failure it is. So all of these simulation right now you're running in either like Solidwork or Fusion 360s. It does not require any failure theories inside. I just want to give you a kind of, a heads up and stuff. Yes, it is actually accurate in terms of predicting in the elastic region where material can recover and then deforms and stuff. But once you pass the yield point where it starts getting into the deformation region, actually all these software can be sort of limit. But I mean, it does give you a proof. You can see some color gradient changes, and then you can kind of showcase, okay, where the forces is majority kind of concentrated at. That's all. So do not get too much over-interpreted of saying, okay, this is the place where it is going to fail. No, it is not. All the conclusion you can draw is simply upon the stresses you're kind of concentrating on that part. So for example, if you're kind of confused, what I'm trying to say is, right over here, you have a 3-point bending over here, and then you're applying forces over here, and then you have a support area, right? So a lot of times when you FEA, you kind of export it, you get these colorful diagram over here, and the darker the color it is, meaning that you have more forces being applied at that area. And then when you get to sort of more blue colors, meaning that that's less of a force. So over here you have more concentrated area. So that's the thing that you can draw a conclusion upon. And again, these FEA model that you're doing, it's heavily considered with some math formula inside. And really, these math formula, you don't see it's running in the background, and you're not able to choose which math theory that it's supposed to fit. and each criteria is actually different. So I caution you when you do these kind of simulation itself. Right, so 5 steps for doing simulation. So this is in Solidwork, and I assume that each of these steps is pretty much the same. It's just probably the procedures is different in different software. But today I'm just gonna open Solidwork, and then we're gonna do some tensile test and bending. So yeah, so material contact, friction, and load and mesh. So these are five steps you have to do to perform a simulation. And for sure, yeah, so for sure, like if you're already pretty much familiar with that, what I'm gonna do for today, remaining 20 to 25 minutes, I'm quickly gonna set up the model and then run it, and then I'm gonna spend the remaining time to kind of answer if any, like I assume some of you probably have questions that want to get answers, or problems you want to get help to solve. So I'll save that time to kind of answer that. So let's kind of. Yeah, so I'm gonna do STM, dog bone specimen, and bending. And yeah, sorry about kind of jumping off. So safety factor or factor of safety. So this is also important. We can generate that in a Solidwork over here. So factor of safety, to kind of give you a more definition of this, is whatever the force you apply divided by the yield strength of the yield point. So I mentioned that the yield point is a important definition, or the terminology you have to remember. So the higher the safety factors is more safer, and then the lower meaning that hey, you're actually passing that point over here. So I'm gonna kind of, if you can see from my screen, this is the yield point over here, right? So basically it's whatever the stress divided by the yield point, and then if the number is higher, meaning that it's more safer, and the number if it's lower, meaning it's not safe and it's about to fail. So you have to keep that in mind. So I'll talk about upper report. Yeah, so this is geometry. I won't, for the STM developer, I'm just gonna draw a strip and then perform a simulation. So I'm gonna pull up Solidwork over here. Yeah. So in the past, if you're in the computer room, usually I'll have you guys to kind of practice and then be familiar with it, and then play around, and then if you have any geometry you want to input, we can talk about it. But since likelihood this semester's special conditions, I'll just do it on my computer. And again, if you can download Solidwork, that would be great, and then you can follow along. And by the way, don't worry like if I'm going very fast, because I also record this video. So again, you can go back and then kind of refresh the memory what I'm talking about. So don't worry about it. So, all right. And this is in Mandarin version, but let me quickly draw a specimen. Yeah, so to clarify right now, I'm just drawing a rectangular, and then I'm gonna extrude it out a little bit. So it doesn't really matter. Let's make this crazy. 0.5 inches. Then okay. So right, so the way that we do the simulation, which is already available in the Solidworks, is we go right over here, and then do new study, and then click OK. Right, so if you can see on the left-hand tablet, and I'm just, my apology over here. So this is basically, you can see the little picture over here. So getting back into what I mentioned is over here, you'll see the parts, connection fixtures, external load, mass, and results options. So this is how you do it. So first thing first is you need to kind of let the computer, let the Solidwork know what material that you're kind of designated at. And let's do aluminum, which is very commonly used. So the 6000 theories, 6061 is very commonly used. Oh yeah, okay. Okay, so with that, so right now you can see there's like a description of you saying 6061 alloy, right? What we're gonna do is we're gonna put some boundary conditions for that. So click that. So you can see like there's like marks going everywhere. So I'm gonna put the boundary condition and I'm gonna explain why I'm putting boundary condition. So I'm gonna click right over here, and then the bottom right now it's fixed. So click OK. Okay, so I don't know. A lot of people get kind of confused about this. Why I'm doing this. So getting back in, I'm doing tensile test, right? And to not to confuse you is that you can think about, you need one side to kind of be stationed on one side, right? And then you do testing on one side. So you're doing a polling, right? What happens is if you don't put this criteria over here and then you start polling, this entire strip is gonna fly on whatever direction you're applying. So again, boundary conditions, which the green line over here is sort of showing over here, is a important criteria that you have to kind of consider when you do your design. Never forget that. So yeah, so over here is where you apply the load. So there's different like kind of forces you can apply. And today I'm just gonna go with simple, with just forces, and then torque, pressure, and then gravity, and then other and etc. And again, when you do simulation, you don't want to try not to get everything so sophisticated. Let's keep it simple. So right, so click over here, and then inverse. So I don't know why they designed like that, but you can apply a force. But we're doing a tensile test right now, so you can see that the arrow is coming up over here, right? And then let's put it at 10 kg or 100 newtons. Let's see. Click OK. All right. So over here is MASH. So so over here, you click right click, and then over here you can generate MASH. So generate MASH over here. And what it does is on the left, like we can turn this icon left or right over here to kind of, so what it does is MASH, what does MASH mean is when you put like more higher MASH densities, meaning that you have more calculations of each of these like inside this geometry. So therefore it's more accurate. And then if you more like go for a coarser one, it's not as accurate as possible. So you know what? I'm just gonna, let's do a more finer one. You get what I'm saying. So let's generate. So you can see that you see a little like square triangle going around here and there. Okay, so I think a lot of people when they do this take it for granted, but I think one of the interesting feature, and then a lot of like research people dedicate their life to kind of do this kind of study. So to give you a heads up that this kind of feature where you do triangles or whatever the qubit stuff is not really the only option you can use. But anyway, take it for granted they already help you do the matching. So let's just take it, you know, considering that's all correct and stuff. And then I think we have everything right. So click over here to run the analysis. So there you go. So the output, so over here it's in, so let me explain this. So over here I'm clicking, basically this is mimesis. So not to confuse you, is this is stress, by the way. So stress is force divided by area. This over here is displaced, moving forward over here, that's the displacement. And then the third one is the strain, okay? Now if I move on to the stress over here it's basically showing a yield strength, that's 5.5. times to the power of 7. So I mentioned that any number that passing this, meaning that it's heading into, it's passing a plastic deformation, meaning that the material will not recover by itself. And you can see these numbers, it's 10 to the power of 5, right? So it's below this number. So basically this design with applying 100 newtons, which is 10 kg, it's safe. Okay, that's this material applying this force is safe. That's not gonna, it's not going to break or pass the yield strength or anything. Okay, so all the stuff I like to quickly point out is what we can do is let's show. So if you go over here and then go into here, there's the factor of safety factor, and then we can just continue clicking on, and then click OK. So it's able to show factor of safety, and then over here it's basically showing the minimum factor of safety of 1.2 times 10 to over here. So that's the minimum number. So it's like 100-ish safety factor. So I mentioned, just to give you a heads up, that usually in industrial design, when in the industrial sector, when I design, a factor more than 6 or 10 is already pretty much safe. The fact that over here it has a minimum number of what, like 100, 1,000-ish. You can see the factor safety over here is like what, 1,000-ish. So this is as much as very safe that the load that we're applying right now. So you don't have to worry about that. And then other stuff we can do is over here. So again, my apologize, this is showing Mandarin, but if you pull up your Solidwork over here, this is like a report basically showing, and then you can output your report. So typically I don't do anything. You can change like your name and then like EPICS or whatever and stuff. And then let's just generate it and see what the report look like. Give it a few seconds. Yeah, so you have a report over here. You can change this later. These are all addable. You can change it. And these are the output numbers. So over here, it's basically showing like the mass and the value and all these stuff. And yeah. So typically, if we're in the computer room, I'll have you guys run this and then, kind of show the output results. But anyway, today I'm just going to do it. And then if you have time, go ahead and then practice this. So let's do another scenario. So still have time. So jump back here. Now I'm doing some bending. So you can see the right-hand side. So what I'm going to do is I'm going to form a bending. So I'm going to quickly draw the geometry. Yeah, so let's make this longer. Let's make this 2. Okay. So finish, you can click finish and then go to over here and then you want to elongate it. So there you go. So let's make this 10. That's too much. I mean, you can play around, it doesn't matter. I'm just arbitrarily drawing a shape like that, like a hinge, if it makes sense. There you go. So you have sort of like a shape like that. Anyhow, so what I'm gonna do is I'm gonna do a bending, like bending this long shape over here. So go to simulations. So over here in the English version, this should be new study. And then here, so I guess I gone quickly for the tensile test. So over here, it's just showing static, frequency, and then so on. Over here, like heat, fatigue, and non-linear, and then etc. So let's just do static. Let's keep everything simple. All right, so again, you right-click over here and then choose the material. Let's still go with aluminum. Use it, then close. So it's going to show up as 6061. All right, so this is the boundary condition I'm talking about, where you want to fix one side. So you can see this is like a bending, right? And show where you want to put the boundary condition. So to pretty obvious. It's over here. I know sometimes it's very confusing when doing this, where you want to put the fixed load, but I mean you'll get used to it later on. And then where you want to apply the load. So right, so let's do it like this. Let's apply the load like this, and then inverse. So applying a load below, right? And let's make it crazy this time. 1,000. Would that make sense? So this is kind of number you kind of think about if it makes sense. Let's do this. Let's see if it can run it. All right. And then generate mesh. I won't change that. So whatever that's inside, I'm gonna generate. So this is very rough, by the way. In the optimal designing these mesh, it has to be on the same size. So you can see some of them are kind of distorted in a way. This is very coarse meshing. So yeah, let's run it. So here's the run button. Let's run it. So yeah, so over here you can see, so the output a yield strength that's, so for Luma again, the yield strength is 5.5 to the 10 power of 7, right? And you can see that we actually reach close enough. This is still 1.38. It's not close. Well, it's 5 over here and it's 1.3. So we haven't really hit the yield strength yet. So this, the load that we're applying, which is 10,000, it's still pretty much safe. Consider this design. So it's pretty good. So now let's move on to, yeah, strain. So one of the things is, again, we can output the safety factors. So go to over here, and that's the safety factors. Click, go on, and then let's see the FOS. So yeah, so over here it shows the minimum of the safety factor is 4. So this might be a little bit you just have to be cautious. So for this is the safety factor right now is 4, right? So as I mentioned, usually they would design like a 5, minimum 5 of 6. It really depends. So it's basically saying on some areas they has a safety factor of 4 that might be, there's something put as a red flag that you want to watch out. So yeah, so that's one thing. And then other thing I want to kind of show you is, let's redo the simulation again. So again, we can kind of delete this and then redo it again. So let's redo this again. And then let's apply a load like over here instead, and then put like 10,000. Yeah. And then so right now it's sort of like a tensile test right now we're doing. And then click OK. And then, so this will pop out something like that. Basically, there's something wrong. So we just have to, because we're right now doing a different scenario, right? So let's redo the calculation. There you go. So yeah, so you can see 5.5. So this is a lot safer. Right now it's only 6, power to the 6 power 7, right? So the way that we apply force on this direction is a lot safer. So one other stuff is interesting enough is, let's do another quick test. So right over here, what I like to show is, let's re-click this. If you go over here, and this is basically a optimal design. So I'm gonna click that. So basically, it generate a, you see the color design over here it's showing. So when we design things, usually you can imagine that we want to be going back. We want to have a lightweight, but still have its strength, right? So one of the things that it do is that it optimize. It help you to do the calculations to optimize. Okay, what is the material that's really unnecessary that we don't need, but still maintain the material strength while we're conducting a force onto it. So over here, basically, according to calculations, this region of area we don't need that. So we can kind of illuminate this area to save some material, or if you want to decrease the weight in a way. And this really makes sense because if you go back to, let's go back to over here. So if you go back to over here, this is actually the displacement, and you can get why they're considering taking off this portion. As you can see, if you can see my mouse moving. So this over here is the region of area where it's so less intense of the force that's being applied. So they consider taking this out so that you can save a little bit more, like it's lightweighted so that you can save. So when you design, you can crop this out if you're considering, but over here it's not because you're applying force at this region, right? So that's why it's not able to do that. So this is also one of the considerations you should consider. Right. So, okay. So right now I have done 2 scenarios and stuff. So let's see. Okay. So as typical as I mentioned, usually I'll have you guys like go down and then practice. So with that, let's see. Okay, let's go back to the manual and then, okay. So I want to kind of talk to you guys if you have any questions you want to kind of raise, questions, anything. If you have, let me type my email inside so that if you have any like questions, like you're actually doing these FEA analysis, and you want to kind of talk about how do you struggle a lot and you don't know how to apply, how to make it function and stuff, go ahead and then just send me an email and then we can set up a meeting individually and then we can sit down and then sort of kind of talk, how do we solve this, okay? So yeah, any questions, quick questions, anything? Good. All right. So what I'm gonna do is I'm gonna still stay, and if you don't have any questions, we can call it a day. If you have, you can stick around a little bit longer, and then you can ask me. But yeah. So thank you for participating for the FEA 101, and then hopefully feel free to contact me. I'm more than happy to sit down and then kind of go over in the details and stuff. Okay.
Thank you for the presentation. I hope you have a nice day.
Yeah, thank you.
Thank you for the presentation.
Yeah, thank you very much. Have a good one.
Yep.
Thanks so much, Tim.
Yeah, thank you, Jacob.